Good day, Adam Harris here with C-Therm Technologies. We were recently asked by a client for assistance in measuring the thermal conductivity of some different fruit materials. I just wanted to review quickly the basic setup for measuring an apple. So basically with measuring an apple, what you want to do is cut off a slice. You want a nice smooth interface to come in contact with the active area of the sensor. Remember that we have to cover the active area, which is about 17 millimeters in diameter. The sensor works by the modified transient plane source method for measuring thermal conductivity. There's some really great webinars on our website describing further how this technique works, but basically it is a single-sided heat reflectance sensor. The sample material is placed in contact with the sensor. The weight on top of it is just to ensure that we have a little bit of contact force there on the sample, ensuring that there's a good intimate contact between the sample and the sensor. But the real important thing in all of this, just from a sample presentation perspective, is that the sample is flat, that we avoid any big pits or significant voids in the sample material, having a nice smooth surface in contact with the sample. So that said, we're going to start the test here. So the first thing the sensor is going to do is initialize the sensor, establishing communication with it and doing an initial pre-firing, and then subsequently in about 15 seconds we're going to start our first measurement. After that we'll take a measurement data point every 60 seconds. So within 4 or 5 minutes we should have numerous sample results here. One thing to consider is you're looking at measuring different agricultural products. One of the really dominating factors in the effective thermal conductivity of the material is the water content of the sample. So this is something you'll want to consider as you present the sample. If, for example, you cut the apple up a couple of hours ago and left it out, it would gradually dehydrate, and so you would have a lower water volume content in the material. And this would likely have the effect of decreasing the effective thermal conductivity of the material. Water is around 0.61 watts per meter Kelvin. So the amount of water in the material makes a significant impact on the effective thermal conductivity. Our first result here for the apple is 0.42 watts per meter Kelvin. We have just taken one measurement. We'd like to take 4 or 5 measurements here and then see a very good statistical average with a relative standard deviation under 1%. So we're taking another measurement now. The test sequence is automated. This is something you can set up and walk away from. But we see really very much a duplicate value here of 0.42 watts per meter Kelvin. If you want to see the raw data for this measurement, you can look at the voltage time plot. And it's the slope of this line that we're using to determine the thermal conductivity of the material. So what you're looking at here is the voltage over the square root of time. The voltage is directly calibrated to a change in temperature, so fundamentally what we're looking at is a change in temperature over time measurement, and it's the rate of that increase in temperature at the point of contact with the sample that is inversely proportional to the thermal conductivity. Stated otherwise, the steeper the slope, the lower the thermal conductivity, the flatter the slope, the higher the thermal conductivity. There's no need for you to actually do your own interpretation of this raw data. It's made available to you as a C-Therm TCI user if you would like, but the TCI software is doing all the heavy lifting here in terms of determining the thermal conductivity of the material. There is no requirement for an inputted density or an inputted CP value. The instrument is directly calibrated for the measurement of thermal conductivity. We see repeated tests here measuring specifically the thermal conductivity. If I focus in on just the thermal conductivity values reported, you can see that the average here after 3 measurements is 0.42 watts per meter Kelvin. So far we see very good reproducibility to that number with a relative standard deviation under 0.2%. We'll let this take one more measurement, and then we'll conclude our characterization of the thermal conductivity of this apple sample. Very good. Again, 0.421 watts per meter Kelvin for an overall relative standard deviation of under 0.2%, showing very good reproducibility to the number. Effectively here, we'll stop the test and share the results with our client. Thank you very much. Hope you found it interesting. For more information on C-Therm technologies, please visit ctherm.com.